Hey guys, today we're going to be talking about the compositions of transformations. And you can follow along with these slides that I posted up on Classroom to go along with this video. And feel free to pause to write down any definitions if you want to write down the definitions on the slides and then put the examples and explanations I put on here. Then you'll have the notes for what we need. So on the first slide, we define what a composition of transformations is. And it's defined as when a transformation is applied to a figure and then another transformation is applied to its image. So this just means we're doing more than one transformation, like maybe we're reflecting and then translating, or rotating and then reflecting, or even more maybe you reflect and then you rotate, then you reflect again, then you translate. We're mainly going to focus on isometries right now and just doing different combinations of them. So that's what the composition of transformations is. It's just more than one transformation that's taking place. Now onto a special type. Our first special type on slide 2, we call it a glide reflection. So a glide reflection, we define this, a glide reflection. It's defined as the composition of a translation followed by a reflection in a line that's parallel to the translation vector. So what this means, let's say we have a triangle. It looks like this, and we'll put point A up here. If we have a triangle, and let's say we are going to translate first, so we're going to translate by, we'll call it vector V. We translate by vector V, and we'll end up with a congruent triangle here. Here's A prime, this was A prime. So our triangles are congruent, this is an isometry. And we are going to then follow this with a reflection, I'm going to reflect right here, over a line that is parallel to the translation vector. So we'll say this line is parallel to vector V, and we're going to reflect over, and we end up right down here. And your A double prime would be here. You're going to be the same distance away from your line of reflection. And this is an example of a glide reflection. So you translate and then you reflect over a line that is parallel to your translation vector. There's a glide reflection. You could have reflected going above as well. Anything that's parallel to our vector. You could even reflect over a line that's kind of going through the triangle, and you're going to see it flip still. All are okay. You just have to be parallel to that vector that you translated by. So onto our next slide. We'll do a little example with this. In this example, we're given triangle JKL. So I'm going to write the points. We're going to have J, we're going to have point K, and we're going to have point L. Point J, that vertex has the coordinates 6, -1, K has the coordinates 10, -2, and L has the coordinates 5, -3. And we are told that we are going to translate along a vector 0, 4, and then we're going to reflect over the y-axis. So when we translate over this vector 0, 4, that'll be our first transformation here. We'll first end up with, well, J prime is going to end up being 6, 3. K prime will end up being 10, 2. And L prime is going to have the coordinates 5, 1. So these will be our coordinates after the first transformation. Then our second transformation is to reflect over the y-axis. So when we reflect over y, we're going to have J double prime, K double prime, and L double prime. When you reflect over y, your x changes signs and your y stays the same. So we'll have -6, 3 for J double prime. We'll have -10, 2 for K double prime, and we'll have -5, 1 for L double prime. These are going to be the coordinates for the vertices of your image after you've done both reflections. or sorry, after you've done the translation and then the reflection. So after your composition here, your glide reflection. All right, so on to our next. We're gonna have a theorem now. So a theorem that we're gonna introduce. We're gonna introduce a couple today. One theorem that we have simply states, and this is on the 4th slide, it simply states that the composition of 2 or more isometries is an isometry, and that just means that your final image is still going to hold the properties as if you did an isometry. So your final image will be congruent. Let's say we had a nice square, call that a square, and if you rotate the square and we end up down here, and then you reflect the square, we'll say over this line, and we're going to end up looking like this, and we'll say this point was the same in all of these. This square at the end is still going to be congruent to the square in the beginning. It's like an isometry. It holds the properties of an isometry. So that's a nice theorem to have. If we're doing a composition of 2 or more isometries, we know our final image is going to be congruent to our original. Now on to another theorem here. It's another special type of a composition. This is in slide 5. It says the theorem is the composition of 2 reflections in parallel lines can be described as a translation vector that is, first off, perpendicular to the 2 lines, and also is twice the distance between the lines. And for this, I'll show you a nice example. Let's say we're going to take a triangle, and let's say we're going to reflect it over line L, then we'll reflect it over line K. For this theorem, we're reflecting over 2 parallel lines, so line L is parallel to line K. And here's how it's going to work. So let's say we have triangle, we'll make a triangle like this, call this P. So when you first reflect over L, remember when we reflect over a line, that line is going to be the perpendicular bisector of the segments, so of your pre-image and image of the segment connecting. So if we actually call this P down here and this P prime, then this segment here is congruent to this segment. That's what we know about a reflection. And let's say we reflect, I'll do this one in blue. Now we reflect over the other line, so we're reflecting the image over our other line here. So we'll end up with this right here. And these 2 segments would be congruent as well. Line K is going to end up being the perpendicular bisector of this segment connecting P prime to P double prime. So what this theorem is saying is, first off, this composition from triangle with point P to triangle with P double prime, instead of calling this 2 reflections, we can relate it as a translation, and the translation vector is going to be perpendicular to the 2 parallel lines that we reflected over, because we're going to be perpendicular for this, we're going to be perpendicular over here. So this whole segment, P to P double prime, is going to be perpendicular to both of those lines. And the distance, and we're going to prove this in a second, the distance from P to P prime, or P double prime, so P double prime, that distance is going to be equal to the distance from L to K. So if we introduce 2 points, A and B, P to P double prime is going to be equal to 2 times your distance of 2 times AB. So the distance from A to B, or the distance between line L and line K, this distance from here to here, the distance from P to P double prime in this case will be 2D. That's what we have going on here. In our next slide, actually in our next, I'm going to erase this, we're going to prove this right now. But you can kind of think of it like you have one little segment here, another segment here, and you're taking both of those and one more of each. So you're going to be double, and we're going to formally go through a proof of this. So you can add the proof to your notes. Here we go. Let's give us a diagram that's explaining everything we have and everything we're going to try to prove. Put a diagram right over here. Hopefully we can fit this proof in. We'll call it line L and we'll stick with line K. And we're going to be given, we'll just use 1 point for this. We'll use point A. So we're going to be given line L, line K. We're going to be given that L is parallel to K. We're also going to be given that A was reflected over L to get A prime. Then A prime is reflected over K to get A double prime. And we'll introduce 2 other points here. I'm going to put them right here. Call this point B. Put another one right here. Call that point C. Those points have significance because, I'm going to get a little closer. Those are going to be the points that the segment from A to A prime falls on, and the segment from A prime to A double prime, that's where it intersects line K at. So we're going to be given those, and we'll say, because these are going to be perpendicular, the segment BC, that's the distance between the 2 lines. So this is the distance between the 2 lines, between L and K. So let's go ahead and write down our given info and then formally prove this. So our givens, might need a thinner marker. Givens, this is better. We have, well, L is going to be parallel to, oh not M, I did K, to K. We're going to be given that point A is reflected over L, and then A prime, and we'll say this gets us A prime, then A prime is reflected over K, and that becomes A double prime. So A double prime is a reflection of A over K, A prime is a reflection of A over L. A prime is a reflection of A prime over K, A prime is a reflection of A over L. Okay. And then we're also given that BC is the distance from L to K. So the distance from L to K, distance between the lines. And our goal is to prove that 2 times the distance between the lines is equal to the distance from A to A double prime. Alright, so let's go ahead and go through this. So our first statement, we're going to need statements. We're going to do a 2 column here. Statements, reasons. Our first statement would be all of our givens. And all of this you can just write in here. I'm going to save a little time and not write it down on here. Alright, so our statement 2. So based upon the definition of a reflection in a line, we know that line L is the perpendicular bisector of the segment from A to A prime. And we also know that K is the perpendicular bisector of A prime to A double prime. We know that by the definition of reflection in a line. So the line you're reflecting over is the perpendicular bisector of your preimage and your image. All right, on to the third. So try to think on your own what would be a good step to take after this. What does having the perpendicular bisector tell us? And what it tells us is going to be that our distance from A to B, that will be congruent to B to A, or B to A prime. So these two are congruent to each other. So it means to be the perpendicular bisector. And we also know the same over here. So from A prime C, from that segment, that's going to be congruent to C A double prime. And that's the definition of a perpendicular bisector. So on to our fourth step now. So based upon these statements, we can simply now say if they're congruent, that means they have the same measure. So we can say AB is equal to BA prime, and we can say A prime C is going to be equal to CA double prime. And that's just the definition of congruent segments. Okay, so try to think of where we're going to go with this. Try to map out the rest of our proof. How can we use this information to prove that 2 times the distance between the lines is going to be the distance from our preimage to our image? So your next step here, we're going to think about that distance from the preimage to the image, and we're going to write that as just a sum of all the segments that make it up. So AB plus BA prime plus A prime C plus C A double prime, that equals the whole segment. So A double prime. And we know that because of the segment addition postulate. So then our 6th step in this proof, now we can do a little substitution. AB is the same thing as BA prime. They have the same measure. So wherever I see an AB, I can replace that with BA prime. And wherever I see an AC, I can replace that with, or sorry, whenever I see a CA double prime, I can replace that with A prime C. So I'm going to use these as our segments to substitute. So that's substitution. And the reason why I chose the BA prime and the A prime C is I can use those to represent our BC, because those are going to make up BC in total. So a little more work here. You can combine, and you get 2BA plus 2A prime C is equal to A double prime. That's more substitution. Then on to our 8th step. We can say 2 times BA prime plus A prime C is equal to A double prime. We've talked about that being the distributive property. And now on to our 9th step. So our 9th step, we can focus on getting this 2BA prime plus A prime C. If we can replace that, we're almost in what we want to prove. And in order to replace that, well, we need to say that B A prime plus A prime C, well, that's equal to BC, because of, again, the segment addition postulate. Which leads us to our 10th statement here. So therefore, 2 times we're going to substitute BC is equal to A double prime. We did that because we can substitution, and then we're all done. And there's our proof. So now we've proven that this relationship is true. From the preimage to the image is twice the distance from one line to the other if you're reflecting over both of those parallel lines in a composition of transformations. So now we can use that. And we're going to do one example with this, then I'll give you some more to try on your own. So let's go ahead and take away all of artwork. Alright, so our example, this is on the last slide that we have. The example says the point A is -2, 8, is reflected over the line L that is represented by the equation y equals 1/2 x plus 6, and then it's reflected over the line y equals 1/2 x minus 4, and we want to find the distance from the pre-image to the image. We want to find the distance from A to A double prime. Okay, so I actually have a whiteboard here. I'm going to pull the whiteboard out. So for this, we have point A is -2, 2, 4, 6, 8. This is point A. We're going to reflect this over the line. We go up 1, 2, 3, 4, 5, 6, and we have a slope of 1/2. We're going to reflect over this line and then reflect over this line here. And we're right about here. So this was line L, and this over here was, I think we'll call it line M. So we're going to reflect over both of these. Now sometimes you might end up with a point that's really easy just to do both the reflections and find the distance. For this, notice that if we want to reflect, we're going to have to find the perpendicular to this, the perpendicular slope, and the perpendicular slope would be a slope of 2. So we're going to end up having a point that's not necessarily the best point to have if we try to do 2 reflections. And also we want to show how we can use this theorem now that we've just proven. So if we can find the distance between these 2 lines, line L and line M, then we know if we reflect A over L and then A over M, the distance will be twice of those. So let's look. To find the distance between 2 parallel lines, you need to find a point on each one. So I like using a y-intercept. And then, well, in order to find the distance, we're going to have to use 2 points, but they need to be perpendicular. So we're going to have to use a slope that's perpendicular. So it's going to have to be a slope of -2. So from this point, I'm going to use a slope of -2 and see if we get to a nice point. Down 2 to the right 1, down 2 to the right, down 2 to the right, down 2 to the right. And this point ends up being on the perpendicular. That would be the point 1, 2, 3, 4, -2. And this would be the point, like the y-intercept, 0, 6. And we need to find the distance between those 2 points. Now you could use distance formula if you want. Since we're on the coordinate plane, I'll just break it into a nice little right triangle and use Pythagorean theorem, which is essentially the distance formula. We go down 2, 4, 6, 8 units. We go to the right by 4 units. So if we make that right triangle, our distance would be equal to square root of 8 squared is 64, and then, or 64 squared plus 16. So it's going to be the square root of 80. So our distance between the 2 lines, we go ahead and simplify this. We should get 4 radical 5. 16 times 5 is 80. So the distance between the 2 parallel lines is 4 radical 5, which means the distance from A to A double prime is going to be 2 times 4 radical 5, which is 8 times square root of 5. So that'll be your distance from A to A double prime. And we're all done. So you can go ahead and try some more of these on your own. I posted some on Classroom for you. I also posted some problems in the textbook of completing different transformations, different compositions of those transformations to see how you feel. And yeah, that's all you have for the day. Enjoy the rest of your day, guys.